Hi everyone, today we are going to discuss regarding Boolean logic, one of the interesting and easy topic which gives you a lot of mark. There is a lot of confusion that this topic is really tough and all, not exactly. If you're clear with the basics, it's really easy to do the task. So I have prepared this slide for syllabus 2023 onwards, but the students who are going to do the O-level, they can also use this. This will give them a clear idea if you are missing a lot with logic gates. So here one thing you need to understand is there in the new syllabus, logic gates or Boolean logic has been moved to paper 2, where earlier it was in paper 1. Also, before learning, you need to understand why you need to learn logic gates or what is the use of logic gates. See, a lot of circuits has been made with the help of logic gates. To make it simple, a lot of electronic components has been made with the help of logic gates. You might have learned regarding SST where it has been made with a combination of NAND or NOR gates earlier, or you might be learning further depending on your school and how the syllabus is going on. But a logic gate is used to create logic circuits. Logic circuits are responsible for making electronic components. Also, you need to understand what is a logic circuit. It is a combination of logic gates. Also followed by how the output of connection of logic gates will be presented, or like how the results will be there. To understand that, we create something called a truth table. The checking of the output from a logic gate or a logic circuit is done using a truth table. So these are the terms which will be mentioned in the whole chapter. So now hope you are clear with like what is the use of a gate and what is a logic circuit. To understand further, we will be discussing about what are the different gates you need to learn. The logic gates which you need to learn in O level include NOT gate, AND gate, NAND gate, OR gate, NOR gate and SOR gate. So these are the basic gates which you need to learn. There are more gates, but it is not relevant for your syllabus. So the first one which we are going to discuss is regarding the NOT gate. NOT gate is also known as an inverter gate, which takes only one input and it has one output. So as the name says, it's an inverter gate. When you input 0, it will give you a 1. When you input 1, it will give you a 0. Now you must understand one more thing. Logic gates work with binary numbers. It can enter either 0 or 1. It can give the output also in the same way. It can give an output 0 or 1. Other gates which you are going to learn here will be having two inputs for each. So like here the inputs are A and B in the diagrams. The first gate which we are going to discuss is regarding AND gate, which has a characteristic similar to multiplication. So if you multiply either 0 with any number, it will give you a 0, right? If you multiply 0 with any number, you'll get a 0. So let's discuss on it. So it will be having two inputs. Either you can off both of them, both the inputs, or you can own one input, or you can own both the inputs. So it can have an input like 0 0, 0 1, 1 0 or 1 1. So any of the inputs which has a 0 will give you a 0 because it's multiplication. So any number multiplied with a 0, it will give you a 0. So only input which will give you a 1 in AND gate will be both ones. Next gate is opposite of AND, that is known as NAND. It is also known as like NOT AND. So first what you need to do is like multiply the things. So 0 into 0 will be 0 and reverse it. Then it will become like a 1. So next one will be like 0 into 1. Obviously it's a 0. Reverse it 1. So here only input which gives you a 0, that will be both 1. Because when you multiply both 1, you will get a 1. But you have to reverse it. Then it becomes like a 0. So entirely opposite of AND gate will be the NAND gate. The next one is an OR gate. When you say OR gate, keep in your mind that it's more like an addition. So if you add 0 plus 1, you'll get a 1. If you add 1 plus 0, you'll get a 1. Now you need to understand these are connections which supply power. right? So if you add two ones, then also you will be getting a 1. So here only input which gives you a 0 will be both 0. If both are off, things will be off. If either of one is on, things will be on. Okay, so it's more like addition. And is multiplication, or is addition. Now opposite of or is a NOR gate, also known as not or. Here you can see add both first, 0 plus 0, obviously 0, and reverse it, you get a 1. Remaining everything which has a value, it can be either 1 1 or 2 1s, right? You will be getting a 0 in the case of NOR gate. Before starting with the next gate, which is SOR, you remember one thing, which is like same 0, different 1. That means like if you have same inputs, you will be getting a 0. If you have different inputs, you will get a 1. So if you enter 0 and a 0, you will get a 0. If you input 1 and a 1, you will get a 0. But if the input is 0 and 1, 1 and 0, you will get both 1s. So easy way to remember, same 0, different 1. So now the three things you need to remember from this particular side is like NOT gate will provide you with the opposite output, AND gate is multiplication, OR gate is addition, SOR means same 0, different 1. This will help you a lot. Before starting any further, we can discuss about truth table. Truth tables are used to trace the output from a logic gate or a logic circuit. NOT gate is the only logic gate with one input. Other 5 basic gates do have 2 inputs, and when you take logical circuits, it will be having more. Let's say, for example, if you're having input as a n, you will be having combinations of output as like 2 raised to n. For example, if you have input like 1, you will be having the combination like 2 raised to 1, that is equal to 2. If you're having 2 inputs, you will be getting a combination like 2 raised to 2, that is 4 outputs, right? Here, let's say, for example, if you have one input, there will be like A, for example, you will be having a combination like on or off. So like 0, then 1. So example for this gate will be NOT gate. So here you can see the combinations have only like 2 of them, like either on or a off. So you should start with off, that is 0, then 1. So a 0 1. If you have only one input, the only gate which uses that is a NOT gate, right? Then if you have 2 inputs, for example, like it will be 2 raised to 2, that is equal to 4, right? The gates such as like AND, NAND, OR, NOR, all these have 2 inputs. So here there will be 2 inputs. So let's say, for example, A and B. So to write the combinations of outputs, you start with the last one. So start with 0 1 0 1, followed by double the numbers which is there. For example, B starts with 1 0, right? 2 zeros, 2 1s. Okay, so start with the last one, 0 1 0 1. Then whatever it is there, double it, 2 zeros, 2 1s. So start entering with the last input. Clear? Now let's say, for example, there are like 3 inputs, then the combinations will be like 2 raised to 3, that is like 8, 2 into 2 into 2. So 2 into 2 will be 4, 4 into 2 will be 8. So here you have obviously 8 combinations. So when you write the combination outputs, you start with 0 1 0 1 0 1 0 1. Now what you need to do is like you have to double it. So 2 zeros, 2 1s, 2 zeros, 2 1s. Then again double it. So in the B that is like there, it will be 2 zeros. Now you need to write 4 zeros, 4 1s. Okay. Now if you take, for example, 4 of inputs, then obviously it is 2 raised to 4, that is like 16 combinations. So A, B, C, D will be there. Start with the last one, 0 1 0 1 0 1, 2 zeros, 2 1s will be on the C, and 4 zeros, 4 1 will be on the B, and 8 zeros, 8 1 will be on A. Just double from the last. So start writing from the last and double it, double it, double it. So start with 0 1 0 1, then if further is there, let's say 2 zeros 2 ones, then followed by 4 zeros 4 ones, then 8 zeros 8 1. This will be the easiest way you can do the combinations. Let's now discuss regarding different gates, but this time with the help of tables. So the first gate which we are going to discuss is regarding the NOT gate. So NOT gate has only one input, that is A, and the input will be starting from 0 then 1. Output is Q, which will be reversed. So 0 will give you a 1, 1 will give you a 0. So this is how the table will look like in the case of NOT gate. The next gate which we are going to discuss is regarding the OR gate. As I mentioned earlier, it is addition. The Boolean algebra for an OR gate will be A plus B. So here the inputs are A and B and the output is Q. So when you input both zeros, 0 plus 0 obviously is a 0, but any other thing will have at least one 1, so the output also will be 1. So if it is 0 1, 1 0 or 1 1, the output will be 1. The next gate which we are going to discuss will be an AND gate. As I mentioned earlier, it's more like multiplication. The Boolean algebra for an AND gate will be A dot B. The input here will be A and B. The output will be Q. Now you know, right? If you multiply any number with a 0, it will be a 0. So 0 into 0 will be 0. 0 into 1 will be 0. 1 into 0 will be 0. 1 into 1 only will give you a 1. So the output will be 1 only if both the inputs are 1. That is the case of AND gate. Now let's see NOR gate, which is quite opposite of OR gate. So basically you can say like the output of an OR gate is connected to a NOT gate. This is how NOR gate comes. So it will be having entirely opposite output of a OR gate. So first add 0 and 0, you will be getting a 0, and reverse it, you will get a 1. Then any other number, there is a 1 present there. So when you reverse the output, everything will be 0. So if you add 0 plus 1, obviously it's 1, and reverse it, it will be 1. If it is 1 and a 0 added up, it will be 1. You reverse it, it will be 0. 1 and a 1 added up, it is 1. You reverse it, it will be a 0. So this is how the output will be. Now the next thing which we are going to discuss is regarding a NAND gate. When you connect the output of an AND gate to a NOT gate, basically it becomes a NAND gate. So it is quite opposite of an AND gate. So first of all, you multiply the value and reverse it. So the inputs here are A and B. If you take 0 into 0, obviously it's 0, you reverse it, it will be 1. If you multiply 0 into 1, it will be 0, you reverse it, it will be 1. If you multiply 1 and a 0, it's a 0, you reverse it, it will be a 1. If you multiply 1 and 1, obviously you get 1, but you need to reverse it, it becomes 0. So here the output becomes 0 only if both the inputs are 1. If you see the difference, in AND gate it gives you a 1 only if both the inputs are 1. In the NAND gate it gives you a 0 if both the inputs are 1. On the other hand, in the case of OR gate, it will give you a 0 only if both the inputs are 0. In the case of NOR gate, it will give you 1 only if both the inputs are 0. The final gate which we are going to discuss is SOR. As I mentioned earlier, if it is same input, it will give you a 0. If it is 0 and a 0, it will give you a 0. If it is 1 and 1, it will give you a 0. If both the inputs are different, like either 0 1 or 1 0, it will give you a 1. So these are the table based explanation for the gates. You need to understand this to do the truth table for further solutions. Now let's go further and we can discuss regarding logic notation and Boolean algebra. So each and every gate do have its own logic notations and Boolean algebra. We can start with NOT. The logical expression for NOT is NOT A, and Boolean algebra will be written like A's complement. So top of the A there will be a line in case the input is A. When you go with an OR gate, if the inputs are A and B, you will be writing like A or B. Boolean algebra will be A plus B. In the case of AND gate, if the inputs are A and B, you will be writing logical notation as A and B. Boolean algebra will be A dot B. In the case of NAND gate, it will be returned as a logical notation A NAND B. In the case of Boolean algebra, A dot B whole complement. In the case of NOR gate, it will be returned like A NOR B if the inputs are A and B. In the case of Boolean algebra, we will be writing A plus B the whole complement. In the case of SOR, logical notation will be written like A SOR B. In the case of Boolean algebra, it will be A B complement plus A complement B. Also, it can be written like A plus B dot, that is basically multiplication, okay? A dot B whole complement. So these are the logical notations. It's very simple. If you are having two inputs like A and B, in the case of OR, you will be writing OR. In the case of AND, you will be writing AND. In the case of NAND, you will be writing NAND. In the case of NOR, you will be writing NOR. In the case of SOR, you will be writing SOR. When you say something not, you have to write the not first, then A. You can't write like A not. You have to write not A. Now let's find the truth table with the help of logical circuit. Here there is a circuit which has three input A, B and C. So obviously you will be having combination of 8 outputs, that is like 2 raised to 3, where it is 2 into 2 into 3, which is a combination of 8. Now there are 4 logic gates which is used here. First one is AND, next one is NOR, third one is OR, and the final one is SOR. So to solve this, what we need to do is like, first we need to label the intermediate values. So you can see here in the case of AND gate, there is two inputs which is coming from A and B, which do produce a output. So there we will be labeling it as P. It can be any kind of alphabet which you prefer. It's just for my preference I put it P. The next one is the NOR gate, which has an input from B and C and has an output. There it is labeled Q. And from P and Q, an input is going to a OR gate which has been labeled to R. So P, Q and R are intermediate outputs which we have labeled for our convenience to solve the task. So it is totally for our convenience we are doing it. Now let's see one by one. So the first thing what we are going to consider is to find out P. So before that we need to input all the values which needed to process. So like we will be starting from C, which is 0 1 0 1 0 1, then there is B, 2 zeros 2 ones, then there is A, which is like 4 zeros 4 ones, right? So to find P, you can see the inputs are from A and B. So what we need to consider is like only the columns which is A and B. So these two columns only you need to consider. So what we will be doing is like, as it is an AND gate, we will be multiplying. Now you look at the last two columns. These are the only places there are both ones. You know, right? If it is a multiplication and there is a 0, you won't be getting a 1. So only these two places, the last two rows, will be having both ones. So in the answer also, that will be the only place we will be getting ones. You can see other ones we will be getting 0. So like whether it is 0 0 0 1 or 1 0, you will be getting only 0. Next we need to consider the NOR gate. So in that case what we will be doing is like, we will be considering the NOR gate, and for NOR gate the input is coming basically from B and C. So B and C are the two places the input will be coming from. So here is B and here is C. What we need to do is like, we need to find out all the zeros and zeros, because in the case of OR gate you will be getting output 0 if both the inputs are 0, but here it is NOR, so it will be getting an output 1 only if both the inputs are 0. So this is the only one which has both zeros. So you see only output which has 1 here is the first row. So that's how we will be finding out our Q. It's a NOR gate, so it will give you a 1 only if both the inputs are 0. Next we will be considering R. When you say R, it has the input from Q and P, and it is doing an OR gate operation. So to find R, what we need to do is like we need to OR P and Q. When you say ORing P and Q, what you need to understand is like if there is anywhere a 1, basically it will give you a 1. So here you can see 0 plus 1, you will be getting a 1. Again here you can see 0 plus 1, you will get a 1. 1 plus 0, you will get a 1. 1 plus 0, you will be getting a 1. So that's how you find the R. Finally what we are going to do is like we will be finding X. To find X, we need to do a SOR operation. And what will be the inputs? The input will be from C and R. So the places where we need to consider here is basically from C and R. These are the places which we need to consider. These columns we need to consider. And when you say a SOR gate, it is basically same 0, different 1. I'm just marking the things which are different, okay? So here 0 is there, 1 and is there, so I marked it as different. The next row I see like 1 and a 0, I marked it as different. There is like 1 and 0 which is different. There is 0 and 1 which is different. There is 1 and 0 which is different. There is 0 and 1 which is different. So these are the places we will be getting a 1. Other places 0 0 1 1 which will give you an output 0. So that's how you solve the truth table. Now let's create a logical expression. Here there is a circuit which has 3 input A, B and C, and there are 3 gates which are like AND, OR and SOR. To create an expression, let's consider logic gate 1 which is an AND gate, and what we will be doing is like we'll be just writing AND there. Then there are 2 inputs which is coming to AND, which is like A and B. We'll be writing that A and B. Okay, that part is over. Next we need to consider logic gate 2 which is an OR gate. We will be writing OR first, then we will be writing the connection with them, that is like B or C. Okay, both of these connections which is out is connected to another gate which is a SOR gate. So basically A and B will be connected to B or C with the help of a SOR gate. What you need to do is like exactly write in the order. So A and B in a bracket, SOR B or C in another bracket. This is how you create a logical expression. The previous one was really easy. Here it is little bit more complicated than the previous one. Here there are like 3 input and 4 gates. So inputs are A, B and C, and the gates are like NAND, AND, NOR and OR. So let's say for example logic gate 1 which is a NAND gate which has the input A and C. So we'll be writing that first. So we'll be writing like A, NAND, C. When you consider logic gate 2 which is having the input B and C which is connected to an AND gate, so we will be writing A and C. Now you consider logic gate 3 which is a NOR gate, and you see there is a difference between the normal way we write it here. You see one of the input is coming from A, other one is coming from an output from logic gate 1. So what we need to write is like NOR A, and basically the other input is coming from A NAND C. So it's basically A NAND C will be done with a NOR A. So you got the idea, right? So one part of NOR will be A, other part of NOR will be A NAND C. So A NAND C, NOR A. Then all of these things are connected with the OR gate. So the first part and the second part will be connected with an OR gate. So there are two parts which will be connected with the OR gate. One part is like A, NAND C, NOR A. Other part is like B and C. Both are connected with the OR gate. So just write in the order. So you can see how it is written. So that's all about how to write the expression. Now all of you need to try an activity which is there in your prescribed book, activity 10.2. Then you will be getting a better idea.